So the two solutions we have currently for addressing this, the first solution is called Post-Quantum Cryptography, or PQC. The background is, like we said before, most widely used public key algorithms that are asymmetric rely on three difficult math problems. The three are integer factorization, discrete logs, and elliptic curve discrete logarithm problems. But the issue is, as I explained before, the development of algorithms such as Shor's algorithm and quantum computers that make these problems pretty easy and trivial for quantum computers. And so PQC is basically an algorithm or set of algorithms that resist quantum attacks because they're more difficult and they're used as security defense against these quantum computers. And so unlike QKD, which is another solution for mitigating quantum attacks, PQC runs on classical computers and networks, making it practical to be implemented today. So the three or the four types of kind of PQC algorithms we have. So the first type is called lattice-based, and it basically relies on the difficulty of using lattices in higher dimensions and figuring out how to navigate lattices in higher dimensions. And this is currently the leading approach we have for PQC algorithms because they're efficient and they're also really strong at addressing quantum threats. And we also have code-based algorithms, which work based on how hard it is to code error-correcting codes. We have multivariate algorithms, which rely on the difficulty of solving multivariate polynomial equations. And we have hash-based, which uses one-way hash functions to create digital signatures and secure against quantum attacks. And continue on to PQC. So the current standards last year, NIST, or the National Institute for the Standardization of Technology, released the final set of encryption tools and standards protecting quantum computers. So they picked 4 algorithms, and these are currently algorithms that companies are advised to start transitioning to mitigating or implementing in their systems. And these algorithms are pretty efficient, and they'll help to protect a wide range of information from emails to e-commerce transactions. And this is also in the process of selecting backup algorithms, and they're still researching others. So by 2027, they're going to have a full paper explaining which algorithms are the most effective and which ones companies should start implementing in their systems. The key takeaway from PQC is that the main pathway forward is going to be PQC because it's easy to implement. It doesn't require any kind of new infrastructure, and organizations should prepare to migrate now because, like I said before, the threat is that companies, adversaries can start collecting data and then encrypt it later in the future using quantum computers, so they have to start migrating now. The second solution we have for mitigating quantum threats is called quantum key distribution. And versus PQC, which relies on math and harder problems, quantum key distribution uses quantum physics and actually physics-based approaches to securing systems. And so basically how it works is it shares encryption keys by principles like quantum certainty and entanglement, and it relies on the fact that measuring a quantum state deserves it so eavesdropping can be detected. And so it also uses the fact that the theorem in quantum physics is called no cloning theorem, which prevents people from directly taking a qubit and cloning it, which then could have break encryption. And so looking at the diagram on the top right, what we have is we have two channels, so a quantum channel and a classical channel between Alice and Bob. Eve is just the eavesdropper and attacker, potentially. And so what happens is that Alice, she sends a random quantum state, a qubit, to Bob by the quantum channel. The receiver, he's going to receive it, Bob. He's going to see, he's going to measure it, and then he's going to return that measurement back to Alice, and they're going to compare which ones have matching bits and which ones don't. They're going to see which ones have matching. And if there's any incorrect or tampered bits, so if Eve, for example, if she looked at the bits, what's going to happen, with a quantum computer, you have a superposition between 0 and 1. When you observe it, it collapses to a certain position. And so when Eve observes a bit in the quantum channel, they're going to know that someone's watching them. And so that bit becomes discarded because they know that there's someone in between. The quantum bit is collapsed, and so they know there's someone in between. And so by doing so, we can tell that there's a eavesdropper, and we're also able to discard that connection if we know there's someone in between connecting. And so at the end, after Alice and Bob verify there's no eavesdropper and that they both have the correct connection with each other, they can then use that key to then connect with a classical channel. And so again, quantum QKD requires both channels. So quantum actually starts a connection and it creates the secure connection between the two parties, and then the classical channel is actually how the information is distributed after. So QKD has different types. So the two types are prepare and measure, which focuses on measuring unknown quantum states, and this can help detect eavesdropping and potential data that's intercepted. And it's also entanglement based, which uses pairs of entangled photons to establish connections. This diagram on the right shows the different layers we have with QKD. So QKD is generally more expensive because you need to create a new layer called a quantum layer. But it's basically the top layer, which is communication between classical channels. Second layer is key management. This is also between classical channels. And the third layer is to actually establish connection. We use quantum channels to actually create the connection, which then allows for key management and communication to occur. So advantages, limitations, theoretically, QKD is unbreakable because it uses physics versus using math or algorithms. And the issue is, though, if it's broken or if there's some kind of mistake in the qubit, it could not work. So that's a limitation. And also, it needs special hardware to run quantum computing and to run these channels. You need to create new hardware and new systems, which are expensive, and they're not currently scalable because right now quantum computing is a very early stage in development, and they're only used for key exchange. The key takeaway is that QKD could really secure high security channels, like government channels, and they really show the power of quantum physics for using or improving cybersecurity.